Welcome back to the seventh lecture on causality for AI and ML. Today we will be looking at causal abstractions, why we need them, what we use them for, and how we define them. So far we have looked at normal causal graphs, most of the time smaller ones, but if you then go into industrial settings, you will find big production processes, and I've brought some causal graph here. So blue are, I believe, the variables which you can observe, which are measured via sensors. The other ones, the red ones, are latent. And now you get this causal graph, and you somehow need to make sense of it. And for that, it would be helpful to maybe not only apply individual causal queries, let's say, like I changed one of these variables, what is the effect of the outcome? Of course, that can be helpful, but maybe we want to like simplify the graph and find more general relations in this graph. So another one, this is even simpler graph, but still it's from a simple platformer game, and it's how the player position affects rewards. There is some sort of planning sequence involved, so it has some time component in it. There might be enemies, power-ups, and whatever in the environment. And maybe we want to figure out from this graph and the data that comes with it, what is the behavior of our player? So it's not it's not obvious from this graph, at least, I'd say. And finally, we might also want to simplify computations. So we just have a simple row of dominoes, of course, as a toy example, but this can get then arbitrarily complex if you compose stuff. And we might want to think of it, okay, what will happen if I tip over the first domino? Of course, the last one will fall. I mean, it's super obvious, but in our structural causal model so far, we would need to evaluate every of those dominoes in between, compute a full chain only to come to this trivial solution in the end. So we might want to find ways to cut out all the stuff in between, like marginalize these variables, but maybe still keep the ability to intervene on the process by doing some smart tricks with the structural equations. And finally, it's also about semantics. So this is these higher level concepts or relations I talked about. So if you get images, well, it's basically an array of a lot of pixels. Every of those pixels can be regarded as a variable. And the question is now, does this particular pixel on its own tell us anything meaningful about the image, apart from its color value at that point? Like, these low-level representations have semantics, but not at the level that we model them. So basically, we would like to simplify the model. We would like to compose variables and merge them together to get meaningful concepts, like the temperature bar that shows in the image, if there's snow, if there are leaves on the ground, and so on. So basically, abstraction is about the granularity of causal models. And there is somehow a way that we can transition between high-level and low-level models. And for that, you can also think of a very detailed physical example, right? Where at the lowest level, whenever you say, okay, I have some atoms, molecules, whatever, they're at a certain position, they move with a certain velocity. But maybe for our application, that's all irrelevant. All we care about is the temperature. And now we need to find a way to transition between these models. So basically, we throw away the position information. We don't need that. We look at all the velocities and compute the energy or the temperature in the system. Yeah. So basically, even though we might have the data on this lower level, we need these models that are useful to us. And in that regard, there's the question, what is a variable anyway? So basically, variables are, yeah, depending on how you define it, there is a lot of debate also in philosophy and whatever, but let's just say they are concepts or values in our models. So at top, we don't apply any meaning or any relation to real phenomenon to them, even though we would like to make our models in a way that they are related. But they might be observed latent, and sometimes there might be helper variables which we introduce to simplify our models, but they are purely hypothetical. So yeah, we can model all of this. The question always is, does it make sense? In contrast to that, we have observables, which are quantities that we can measure. But the thing here is, how do we measure them? Like, which tools are available for us? Are these measurements on the same level of our variables that we would like to model? Basically, what we want to do is we have some measurements which are maybe given, which we might not be able to control. We put that in some sort of causal model, and then we need an additional transform step that transforms these models into the right level of semantics or abstraction. Yeah, so as I said before in the examples, we want to reduce model complexity. We might want to reduce computational effort with that. And we might want to obtain high-level insights. And I already hinted at this a bit. So there might be different operations that we want to do to our causal graphs. So the first one is the marginalization of variables. Basically, if there are intermediate variables or things that we really don't care about, we want to remove them. Then we might want to cluster or group variables. So basically, this is a bit new, maybe. So now, before we talked about variables with like single values in R or some number. Now this grouping operation pulls all of these variables together, and we get a vector valued variable. And here the problem is, and we will see this later, that we just have this vector of variables, but we don't know anything about the causal relations in this group, or yeah, within this variable. So we lose structural information by doing so. And finally, we obviously can transform variables. Yeah, either first group, then do a transform on a single variable, or we like take multiple variables, take the average, for example, with this temperature example, we could think of, okay, first we marginalize all the positions, then we group all the velocities together, and finally we take the average to get some sort of energy vector or whatever. Yes.
So when we're missing information. So if we have, say, a partially directed path, maybe grouping could be a solution if we don't really care about the
yeah. So the thing is, by removing or by grouping variables, of course, you get rid of these partially directed variables. The problem is it doesn't really help us with identifying causal effects, because now you are in a worse situation, right? So I will have an example on this, but basically now you don't know if in this structure there might be a collider or not. So you make the situation worse because now if you want to do a causal effect estimation, you need to iterate over all possible like graph structures within this group. But yeah, we will come to that. That's a good point. So far I showed you, okay, how to make things simpler and easier. Of course, there are ways, or like in theory, you can make models more detailed. The problem then really comes with the observables because you only have so much data. Of course, you can model your SEM to like super high detail, but that all doesn't help you when you don't have the data to fill it. So most of the time it's in the other direction where we say we want to simplify causal models, but we will see that in 2 weeks. There are ways, and then you apply some constraints to these models and equations to also infer latent variables and latent structures from observational data. Yeah, so maybe looking at the groups of variables, so we can define arbitrary clusters of variables, like the red, green, whatever. And so if we aren't careful, a lot of things can happen with that. So first of all, we might induce cycles. So from the red to the green, to the blue to the green one, or between the yellow and the light blue one, we get cycles. And if we see these cycles, it's a bit of a maybe not problem, but we still know or assume most of the times that the underlying graph is acyclic. So if we want to like do causal effect estimation again, we need to be aware that, okay, we can resolve, like put back 2 variables for the light blue one, but then we need to direct the edges in every possible way that could be imaginable from this graph within these groups. But we need to be careful or again reject, like we did in the last lecture, all the causal graphs that could form a cycle or are not a cyclic in the lower model. And another thing is that we can get paths in the high-level model which seem to be closed or seem to have an effect, but which are open in the or non-existent in the low-level model. So you see in the red group on the right, we have 2 variables which are in the same group, but which are not connected. So basically, if I go from green to red to blue, there's no causal chain in the low-level model. Yeah. And yeah, there are some works, especially with these cyclic causal models. There's then something called sigma separation by Joris Moy and others. They have a series of papers on that, which define how separations in these cyclic graphs are defined, which is a bit more tricky than d-separation. But it is possible, but be aware that we might get these models, but then need to take care of some effects that might happen. Yes. That are not connected in the so why you would do this? Yeah. Yeah. So the thing is, these groups might not be defined when you already know the causal graph, right? So you might have something where you know, okay, I have a group of genes that affects another group of genes or whatever, like some expert might tell you. You put them all in these groups and do your causal modeling and causal discovery. And in the end, it turns out, okay, I get these groups that are disconnected. I still want to talk about the high-level model because the low-level one is way too complex to the public or to other people. And Yeah, so you can also think of this, maybe it's objects in a scene, right? Maybe in the red one, it's the shape and color of an object. They might, I mean, you can argue sometimes things are causally related, but maybe you have a setting where they are not. You still want to group them somehow because, I don't know, the green object or the red one is the one that you can control or can intervene on. Um, so yeah, these groups might not be aligned with your causal modeling. So here, the second paper, really, I think it's too much for this course, but you can go into it and have a look at it. So they really specifically target this scenario where you can have all of these weird groups and stuff and still try to figure out what types of causal graphs you can discover, what you can say from the data. Yeah. So maybe we'll look at a very simple model, which is the one where we have some diet that we maybe describe to a patient. Then we have the total level of cholesterol in the blood, and we measure like the strength or the occurrence of some heart disease. And we take this model and we get conflicting evidence. So some studies in the past then showed, okay, the total level of cholesterol lowered the chance of heart diseases. And some other studies showed that it increased the number or the probability of a heart disease. So what do we make of that? Basically, what happened is people looked at this data, and after some time, they identified low density and high density lipoproteins, which basically are both cholesterols. And the problem with the prior model was that we only could measure them together. So we get the more coarse, the abstracted total variable, but the high density lipoproteins, they reduce a certain heart disease and the others increase the chance for it. And I think there are, of course, several heart diseases, and depending on which one you increase, it also has different effects on that. So generally, this is a case where where the model was simplified too much, so that we couldn't identify the true causal effects, or it was too imprecise to measure the causal effects. Then maybe a brief note, because we talked about also marginalizing variables. And if you have non-deterministic models, you need to be a bit careful. So this is basically with Bayesian networks. Because if you remember structural equations, we usually say, well, they are more or less deterministic, but maybe there is a noise term in there. So if I now have a non-deterministic equation from A to B, so it's B is, I don't know, 5 times A plus some noise terms, some Gaussian noise, then you can't, or you can marginalize the variable B, but you need to be careful to not, then if you compose the variables, the structural equation C and D, to not copy the noise term, right? But you first need to factor it out first. So you only sample it once. Then have this M2 causal model, which has an explicit notion of this noise term, and then you can marginalize it out so that the noise in CNT stays the same. Just a quick note to not make this mistake. Yes. Okay, so we talked a lot about, okay, why do we want causal abstractions? How should they look like? What do we want to do with them? Basically, it's a sort of irreversible process. It loses information. Maybe that's actually something that we want to be able to deal with the complexity. But it might be nice to have a more formal definition to apply and really define what we mean when we think about causal abstractions. And we can think of a causal abstraction as a mapping between a low-level and high-level model. And so typically in the literature, we have some function tau and some function omega. And what they do is the tau function maps variable values of the lower level model to the higher level model. And the omega function maps sets of variables from the lower level to the higher level. So basically, if we intervene on some variable on the low level, maybe it affects multiple variables on the higher level, or the other way around. If we intervene on a set of low-level variables, let's say we intervene on the shape and color of an object, but then we grouped it together to one single high-level variable, we somehow need a function that tells us how these interventions transform. And more generally, we want to have a sort of consistency. And so the first requirement that we have is that our map needs to be, or the map of the variable values needs to be surjective. So in plain words, it tells us for every high-level configuration, or like values of high-level variables, we need to have some configuration of the low-level variables that makes them happen. So we always need an explanation on the low level that could explain something we see on the high level. Basically, it's, or you can think of it that there can't be a high level variable configuration that is not supported by your lower level. For example, yeah, I don't know, maybe negative temperatures in Kelvin, right? You can't have negative energy or something. So you need to be sure that your high level model somehow is consistent with the things that can happen on the lower level. And the second thing is the consistency of intervention maps. I've written this a bit, not vague, but so usually people put probabilities and stuff around that. Basically, what this means is that if we intervene on our low-level model here on the left, and then map this low-level model to the higher level, so then apply the abstraction, it should be the same as if we first map both our low-level model and the interventions to the higher level, and then apply the interventions there. So a bit more formally, right? So tau needs to be an surjective map. Omega needs to be some function between interventions. And basically, the following diagram needs to commute. And this is really the property, the last property from the last slide. So no matter which path we take from the probability distribution of X to the intervened on Y, so X is the lower level, Y is the higher level causal model or variable configuration. It doesn't matter if we first intervene, then abstract, or if we first abstract and then intervene. Are there any questions on that so far? Because this is the concept we will use for the rest of the course. Yeah, so aggregation, so that's really this property. Maybe you have to see an example or work through an example. So basically, this surjective map doesn't prevent you from like grouping or like commute, yeah, like grouping or merging together variables, right? Because if you take the average of some variables or whatever, then it really just tells you, okay, there are some variable configurations on the lower level that lead to this or that average. And with the grouping of variables, it's even stronger because it's not only subjective, it's just a bijective map, right? If you don't transform anything, but only want to have these vector valued variables, then it's really just, I mean, you list all the variable values in a vector, and you could even reverse that. But yeah, for this averaging and so on, like it only needs to go in one direction. Yeah, so exactly. So I mean, the thing is maybe assume you have a low-level causal model with three variables, and your high-level causal model is the average of that. So now you say, okay, I can intervene on the first, second, or third variable on the low level, and I can simply do that on the low level and then abstract, right? Set one of these variables to 0, for example, and then take the average of the other two. Um, but what I could also do is to have first my abstraction, but what I then need to do basically is with the do operator to reason about what this would mean in my higher level model. So the thing is, with these restrictions, not all high level causal models are allowed, right? So there might be yeah, some models where we lose so much information that we can't reconstruct our interventions. You're right. So in that case, maybe we would need to like either keep these variables or we would only need to allow a certain set of interventions, maybe setting all of these variables to 0 or something, right? Where we then know what the outcome of the high level variable is. So that's in the original definition of causal abstractions, that's actually done. So I haven't written this here, but basically what they say, okay, we only allow for a particular set of interventions where we know that we can soundly apply them in the high level. Yeah. So, like, I mean, for a general function, you could drop all of those, right? And then get some arbitrary function that does whatever to your causal model. But what we want is an abstraction function that somehow makes sense and that preserves like the causal relations in our model. Yeah. Thanks for the question. Yeah, and so we actually talked a bit about that. So there are some properties that you can define for these causal abstractions. So basically, this is how causal models developed. In the beginning, they also were defined in terms of a very specific exogenous noise distribution. And some people argued, well, these distributions of exogenous variables, they might be chosen in a way that maybe some effects cancel out so that our tau abstraction still seems to make sense. But if maybe we change things, we have some other distributions, maybe our causal model becomes inconsistent. So they required these abstractions to hold uniformly, like under any possible exogenous distribution. Yeah, then as you said, there are also strong causal abstractions, which basically mean that all sets of interventions should be allowed. This really, as we figured out, really restricts the stuff you can do with causal models, because somehow you need to always be able to map interventions to the high level model, and that might require that you know of some aspects of the low level model, so you can't lose them, otherwise you can't soundly apply your interventions. So this somehow prevents cherry picking of intervention sets. And all of these, they are optional, right? So if you are in a setting where you know you have some sort of specific exogenous distribution, or where you know, okay, I will only do these 3 interventions, then it's totally fine to abandon these properties, because they usually help you to define simpler models. Right. Then there's something called constructiveness, which basically tells you, okay, if I have my low-level set of variables, I want to form my causal variables in a way that every low-level variable only goes into one of the higher-level variables at most. So either we marginalize them out, or like we group variables in a way that the high-level variables don't overlap in their sets of variables what they were computed from. And yeah, finally, we have this natural intervention mapping. And this basically is what we somehow talked about before. If you look at this omega function, I mean, we already have our tau abstraction, and it somehow tells you how causal variables or values of these variables should be mapped from the low to the high level. So the thing is, our omega function is somehow constrained by that, right? So we know if I set some variable to value of 5, how this should translate to the high level system. So if we still have this variable there, and maybe it's multiplied by 2 via the tau abstraction, we know if we do whatever intervention on that variable, like it needs to translate in this way, where we also multiply this intervention value by 2. So yeah, and depending on if you have uniformity, strong interventions, and so on, this the omega function is more or less defined in terms of tau, because it tells you how to map these intervention sets. Yeah, so far we have looked at perfect causal models, but in reality, usually our abstractions are yeah, maybe a bit noisy or lose some information, and due to that, maybe the 2 paths might not like align perfectly. I mean, that's simple. Maybe in practice we say, okay, as long as we are like roughly in the same range, so that both of these paths, first intervening then abstracting, or first abstracting then intervening, somehow get us to the same value up to some error, then we are fine with that. That's usually what is done in practice, right? So maybe you are looking at images, and maybe there is some noise in the image, and whatever, you want to measure the height of some object, and due to this this pixel noise, you get a estimate on the higher level, which is a bit biased or somehow differently distributed. Then it might be still okay if we know, okay, on the low level we change the height of this object, or we place something on top of it where we know the exact height in theory on our low level. That due to this noise, we might not observe this exact value in the image, but maybe get some sort of error. So just a note on that in practice, this is usually used. Okay. And then since we talked about clusters, yeah, I think this is the thing that is most interesting then for causal inference. So basically, we only look at abstractions now that only do a clustering, that do not transform or merge these variables, but maybe we just get some sort of set of variables set, and maybe we can only condition on all of them or on none of them. And yeah, so the question is, as it was asked before, can we still compute all the causal effects? And what we need to think of it, and it's pretty obvious, I believe. So if we have these two graphs on the left, and we group all the set1, set2, set3 variables, we need to think a bit about how do all these arrows change. And basically the idea is if any of those variables has an arrow to any of the outside variables, this arrow will still be there. Again, if it's the other way around, so we might get arrows which are in both directions. So this the cyclic stuff. But yeah, basically it's really we take the union of all the arrows that go in or out, in or out of our group, and just merge them into this higher level group. Yes. So in this kind of sense, or at least in the work that defines these so-called cluster DAGs, they have an additional assumption. So they say, well, we also want to avoid our high-level graph to be cyclic, because then all sorts of things can happen. So they say, okay, a partition or like these groups of variables are admissible if the resulting high-level graph does not contain cycles. And yeah, other than that, we really do this thing. Okay, if there is some variable in our cluster that has an edge to some variable outside of the cluster, then this edge will also be present in the high-level model from our cluster variable to this other variable, and the other way around. Yeah. So I mean, we already had that with partial effect identification. Basically, what we need to do is to look at all the possible DAGs that are compatible with our cluster DAG. And the causal effect needs to be computable or identifiable in all of these DAGs. So they usually, or in this paper, they require the effect also to be identical for all of these DAGs. Of course, if it's not identifiable, or if it's identifiable but not the same for all of them, we just at least can do a bounding, right? We can say, okay, what is the best and worst, or lowest and highest causal effect we can obtain? And maybe that at least gives us some information. Yeah, an immediate result is if one of these graphs is or has a structure where we cannot identify the causal effect, then we can't say anything, because then we just don't know if if the true underlying causal structure might be exactly this one graph that we can't identify. So anything can happen there. Right. Yeah. So this is really the other way around. Yes. So we can take the two models on the left, merge them into the model on the right. But the other way around, there might be also the possibility that the variable set2 is a confounder. So it might also be compatible with this cluster DAG or this group. Yeah, and then another example from this paper. Basically, we can start out with the causal model on the left and do different groupings of variables. And depending on how we do that, we might still obtain or preserve identifiability or not. So if you consider the left graph, you see that we can both apply the front door and the backdoor criterion. So we have this intermediate variable S that allows to do front door identification. And we, although it's a bit tricky, but if we condition on B and D, for example, we are able to block all the backdoor paths. So yeah, we could apply backdoor adjustment. And now, actually, if you merge all these variables above X and Y into a single group, then this property might also become a bit more obvious that front-door adjustment could still be possible. And if we choose the groups wrongly, then in C, the effect is no longer identifiable. So basically what you see here is that I believe S and V were merged together into W. And so you get this weird effect from W to Z. And yeah, if you now condition on the whole set W, you might open a path there or yeah, so if you apply do calculus and whatever, you can't really find a way to identify the causal effect in there. And finally, and this really applies only to this very specific paper, in D we made a graph that contains cycles. So from X to W to Z, you see we have the cyclic relation. Are there any questions? So basically, the idea is that whenever you have these groups of variables, you assume you can only condition on them, like on these grouped variables altogether or on none of them, but you can't target variables independently. And then you might still know about some surrounding structure. And the question is, does it help you in identifying the causal effects? Yeah. Yeah, then that's no longer possible in this cluster DAX. So you can, I mean, you can still intervene on X and Y and so on. Like you can also intervene on these groups and it will cut the parent relations. But you can't pick individual variables within W or within Z. So either you cut all of the parents of all of the variables in this group or none of them. Yeah. Okay. Then there is maybe some minor detail. Before we talked about marginalization or marginalizing variables in this sort of models. And basically what that means usually is that you, in the Bayesian networks, pull together all your conditional probability tables, or that you stack all the structural equations of variables together and maybe then simplify them in the consequence. But in this sort of simple models, we can still simplify and retain our ability to intervene. So I think it's really clear that, well, the last domino will follow the state of the first one. So either if it's tipped over or not. But if there is an intervention along the way, so if we tip over or hold on to any of the intermediate dominoes, then the last domino will take the value of this intervention. And this is a bit imprecise, or it really depends. If our set of allowed interventions only allows for a single intervention, then this would be right or correct. If we could tip over or hold on to multiple of these dominoes, then here we need to select the intervention which intervenes on the furthest domino that is nearest to the end, right? Because that's every intervention cancels out all the effects from before. So the interesting thing here is basically that now our interventions, our structural equations, if we do it in that way, now have some notion about the interventions that are present in the system. So if you think of, for example, instrumental variables, which are like special variables that we can attach to our causal graph to indicate whether there is an intervention or not, it's basically something similar here. So what you can think of is that you introduce a new variable I, which contains the current set of applied interventions, and then really is a parent of this last variable. But yeah, the cool thing here is that we can do reason within the causal model about the interventions that are present. And if you take this a step further, you get all sorts of first order logic in there, which really then helps you to simplify your equations. Okay, then let's continue. So as a last part for this lecture, we will look a bit at learning of or with causal abstractions. And basically, the goal that we want to have, or the goal that we want to achieve, is that we have some sort of low-level data. Maybe we have some high-level information, but we might want to automatically discover our abstraction tau and maybe get the structure of this high-level model. And the problem that we usually face is that if we apply some machine learning approach or whatever to learn these abstractions, unfortunately, the trivial abstraction, where the model just maps everything to a constant, is a valid causal abstraction. So this is usually what models converge to if we don't apply any further restrictions. And unfortunately, it's uninformative. Really, mapping stuff to a constant doesn't help us here. So we need to apply some constraints, and this is also then the topic of causal representation learning, which not only learns this abstraction, or then called mixing functions, because they think of it the other way around, that you have an underlying process and want to only observe some outcome by a mixing of variables. But we assume in this setting that we know which high-level and low-level variables we have. In causal representation learning, we might not even know what our high-level variables or latent variables are. So So there is at least one approach I want to show you. So mostly causal abstractions are often used for causal inference, for analysis, for transforming models. But there might be some benefit for causal discovery. Basically, what you can think of is that you might want to go and say, okay, I have some or a lot of low-level data. I have a few data points or some smaller data set where I have low-level and high-level data paired. So for every low-level observation, I have a high-level observation. And I might want to use that to improve or to improve my causal discovery. Basically, what you could try to do is to mine some high-level causal model out of your data. And then because what we discussed before, causal discovery might be a bit brittle if you have like bigger models. You want to use this simpler and maybe therefore more exact high-level causal model to constrain the discovery on your low level. And this is exactly what the authors do here. And I just give the high-level idea. So they assume, I believe, linear a linear mapping between the low and high level. I'm not sure if this is required all of the time, but they prove some sort of theories with it. You can think of these clusters here at the bottom to be things that affect my high-level variables, and a subset of those clusters then directly is used to compute these high-level variables. So, for example, x3 and x4, x7 and x8 go into y1 and y2. Then we have our mapping, so we know maybe the linear factors that compose these y variables. And we can now take all our big low-level data set and map it to the high level. And now it's really straightforward. We apply on the high level some causal discovery method. Here in this work, they used Lingam. So really, it assumes that we have non-Gaussian noise in this setting, at least. But whatever discovery method you use, you will get a causal graph. So here it's really simply that chain. But what this tells you then is that within these clusters of variables, maybe they are given in a way, you know, okay, all the orange ones cannot affect the blue ones. The blue ones cannot affect the red ones. So from this high-level structure, you at least know some constraints or some errors that cannot be there in your low-level model. And the thing that is left to discover is which specific variables of the blue ones affect which variables in the orange ones. So basically, this high-level approach gives you some constraints, which makes your causal discovery on the lower level more robust. And as said before, this really requires that you have some paired data set that maybe some expert or scientist went and recorded both perspectives for at least some data set or for some data that is then sufficient to approximate your abstraction function or your mapping from the low to the high level. Yeah. Then there are further approaches, and we won't go into the detail here. Basically, you can leverage predictability between time steps. So what you can say, okay, if I map from the low to the higher level, and then advance them in time. It should be the same as if my low-level system advances in time and then I abstract it to the higher level. So it's the same, this commutativity property, but it's not via interventions, but induced over this time series. Still, there might be a problem that your causal abstraction or your model still learns to just abstract to a constant function. So what they use in this paper, and so what they basically use is that you can invert tau, so that you can do a sort of autoencoding thing or mapping, where you can also map from the high level to the low level. So with that there come a lot of implications. Basically, what if you would like to require it to be a perfect mapping between low and high level and also the way back, right? This implies that your abstraction function is bijective, that you can like fully invert it. If not, then you have some sort of like noisy auto or lossy autoencoder. Then you really in practice need to balance like how much or how bijective do I want my tau abstraction to be. And basically it's a trade-off between the complexity that you allow in your high-level model and the ability to reconstruct the low-level model, right? So another thing is that you can leverage some learning signal of a target variable in your high level. So maybe you can say, okay, I abstract low-level data to my high-level model. I don't know how it looks like, but I know at least one variable, maybe some class or some value that I want to regress. And I need to be able to discover or to predict that target variable from my high-level model. So it's no longer sufficient to only to only map to a constant function, but we need to preserve some sort of information there. And you can also think of this in the way with the bijectiveness before, because your high-level target variable, you could also think on to have it on the low level, right? And then it's really how much information does tau preserve, how invertible is the whole thing. And finally, there is a rather new paper. This is then really this case where they think about identifiability again and really formalize the way what it means to have different low-level interventions which are not distinguishable on the high level. So basically, you do some interventions on the lower level, but it has the same causal effect on the higher level. And this property tells you something about how much information you lose in that abstraction process. So really it tells you, okay, I'm losing structural information, because if I had a perfect like one-to-one mapping, I would see differences in these interventions. So it's rather formal, but can be helpful if you like think of identifiability results or similar things. Yeah. And then, as I told you before, there is this whole thing about causal representation learning, which basically tells you, okay, I have some sort of observations, maybe the images of the thermometer we saw before and the tree in the background. And really, a priori, I don't even know which of these pixels belong together, which of those form like meaningful concepts. And that might not only be color or shape or whatever, it might be the temperature reading or whatever you see in the image. So basically, how can I learn high-level causal variables from data which are meaningful to my problem and still adhere to the causal dynamics that I see in these images or in my underlying process. And yeah, this, as also already told you, then requires some sort of constraints, because usually what you do then is to have a sort of mixing function where you say this mixing function is somehow autoencoding or bijective. It also requires you to have sufficient variability in your data, because if you have some variable which is always fixed in your data, which does never vary, then you can't infer a causal effect from it, because you like always only have the same value. You don't know what happens if it changes. And on the same note, you also cannot find if maybe under some different setting of your environment, this variable might change if it's always constant. So it has a lot of constraints, but this is then actually the stuff we want to do, or we would like to do, to figure out causal structures, high-level causal structures from images. And yeah, we will come to that in 2 lectures. So I think that's it for this week. Next week, I will not be there, but Florian will tell you first a bit about ML models which leverage causal graphs. So basically, we don't want to discover causal graphs from data, but we use, for example, an autoencoder or an VAE and implement some causal structures in there to make them more causal, to make them more truthful to the underlying causal process. Yeah. Then thanks for your attention.